have another person. We have already know what Moshe is working. We know what Orna is working. We have Bernd as well. Bernd will actually talk later about hyperproperties, but hyperproperties are also relevant. We both mentioned them for a security analysis and reactive synthesis. So let's start. So who wants to? Shall we continue just discussion? Okay, please.
I have a follow-up question on the discussion. So I worked a little bit with opacity in supervisory control. So there we looked into we can handle arbitrary LTL specs, but we have this notion of revolution, and there's current state opacity where your hiding objective is you want to make sure the secret is not revealed at the point it happens. Then there's k-step opacity where you want to make sure the secret is not revealed within k steps, and that k is usually things get very ugly in terms of complexity in k. Then there's also a notion of eventually the secret is not revealed. I think when you have this finite specifications,
Yes,
there are interesting notions of when the secret is revealed as well, and that gives you a richer set of specifications. Any thoughts on that? Because when it is revealed becomes a part of the specification as well.
So the closest thing I have in mind is the work we had about informative prefixes in violation of safety properties. So it has to do, yes, perhaps the secrets shouldn't be finite, but should be safety properties. And then if they are, no, but then they should be both safety and co-safety. Yes, they should be bounded. So even if it's not LTL on finite prefixes, then the satisfaction value. So bounded properties are the intersection of safety and co-safety properties. And in bounded properties, every property should have a finite prefix after which you should be able to evaluate it. So that would solve this issue.
So, I mean, this discussion is, of course, quite old in security, right? There, the three dimensions of secrecy, right? So I think we should distinguish. There's the secret as such, which can be finite or infinite. Then there's the point in time when the secret should be kept a secret, right? There's the notion of declassification, for example, when we no longer care about the secret being kept secret. And then there's the point in time when the secret gets revealed, which, as Moshe said, is after a finite amount of time, right? But you can restrict all these three different types of periods independently of each other.
So yes, this is related to declassification. So after you declassify the secret, then it's like when you enter your password, right? Then the secret is revealed to you, right? And then you can observe all the. So from that moment, the observations do not have to be. So your executions do not have to be observationally deterministic after declassification.
You look unhappy.
I didn't understand that. I didn't understand the difference between the last two things that you said.
You keep the mic. I mean, musica should.
It's good for me.
Sorry, the last two things, you mean declassification and the point of revelation?
Yeah.
Right. So declassification may or may not occur. It just means that there is a point in time where I no longer care about something being secret. Like if you have your easy chair system, there's a point of notification. Afterwards, I don't care about the review results being kept secret anymore, right? And then there's a point in time when knowledge occurs, right? Knowledge means that if there was a difference between the two situations, I would have observed it before that point in time. Only when that occurs, then I distinctively know the secret, right? And of course, declassification means that if there is such a point in time where I acquire the knowledge, then it should be after the declassification point.
Thanks.
This is good for me. This is good for me.
So you spent most of your time talking about the sort of knowledge-based notion of secrecy, which I think most people in the security community would say, well, that's way too weak. That's not what we're interested in. I can be 99% sure of the secret and still satisfy your definition of secrecy. So you sort of mentioned when you started talking about the inequalities in the numbers towards the end, that sort of probabilistic notion of secrecy is much more of interest. It wasn't clear to me whether you actually have any results on that.
So you hear me, right?
Yeah.
So we have two results about the stochastic settings. One is when you add multi-valued specifications and secrets, then yes, so now the satisfaction value of the specification is the number between 0 and 1. If you have a stochastic setting, then you are going to talk about the expected satisfaction value. So this is one probabilistic setting, and in this one we do have, but the one of the probability of the secret whole being true or false, this is something we haven't studied yet.
Can I actually ask now, what are benchmarks that you are having? I mean, this is really impressive work, but maybe can you ask about? Can we ask about the benchmarks and the examples on which this was tested? Because I think this goes nicely with the Moshe's comparison. All this is beautiful, but the complexity is high. So how far we are from theoretical foundations to the real world system?
So we have no implementation of this, so I don't know. The stories that we are telling are from a medical, queuing in medical and banking and cloud and things like that, but we don't have implementation.
I have a question. There is a buzzword that I expected to hear and didn't hear. Multi-party computation.
So it's a good question, yes. So I mentioned the distributed systems, and that we will move on to distributed systems.
But even in a two setting, multi-party computation is, I want to know what is the thing. I want to know who is richer, you or me, and how can we do it without revealing our true wealth, right? I mean, it's kind of the classical things.
But this is something you can model. If it's just too...
but
once you move to the multi-valued setting, yes, it will be a special case for two.
But there's a whole machinery of multi-party computation that people have developed to do these kind of things, and one would think that it might be useful.
Yes, yes, that's why we want to move to natural numbers in order to model this.
Actually, I want to go with what just Moshe asked and ask the following. So in reactive synthesis, you have a spec, right? And the spec says like, okay, do this and so on. And now, let's say I synthesize the program and Bernd, but we actually don't want to reveal what kind of secrets we were using. Maybe we use, is there some work also done that, okay, I created the program that satisfies your spec, but I don't want to reveal the program, but can we use some of these cryptographic primitives like multi-party computation, zero knowledge proofs to actually convince you that I indeed satisfies what you're asking me? Is there some work done in that direction?
As far as I know, not for ongoing behaviors, but this is what the people in cryptography do.
Okay, that's
Rujitsa, I think you want to answer your own question, don't you?
No. I'm just asking, like, and looking at Vardi, we are extending our grant proposal. Okay.
First, you have to write it.
No, but now we get material.
But the work of Boaz Barak in cryptography, this is what they do for general software, but not for our kind of specific.
Okay, let's continue then.
I guess kind of related to the benchmark and multi-party stuff. So I think there's some like simple examples like that in cryptographer. I don't know, can you, like try to cover that case or something like that, using the framework? I guess not, because that's you do need some kind of probabilistic notion, probabilistic by simulation, I would say.
So actually this type of probability, we do have something to think about. It's like another work that Moshe and I did once. We worked about reasoning about infinite state systems, and there is this classical question of the 3x plus 1. You know, so there is x, and given some integer x, if it's odd, move to 3x plus 1. Is there a? It's very easy. So if it's odd, then you move to 3x plus 1, and if it's even, you divide it by 2. And it's a famous open question whether for every x we eventually halt and halt with 1. And we say, okay, now we know how to reason about infinite state systems. Let's apply it to this system, and with the specification eventually 1, and see whether it always halts. It's not that easy, because you have to work with base 3 for the odd and base 2 for the even. We didn't manage to do it. If we had, we would have heard of it. But I wonder whether it's the same here. That yes, all kinds of.
What I'm asking is much easier problems.
Yeah, that's why there may be a positive answer. Yes, but yeah, still we are with our automata and the things we can model with them. But possibly, yes, it's something to think about.
I think I have a more general question, also a bit of change of context. So a question for all of you. We briefly mentioned that environment is adversarial, so also the environment can change over time, also the behavior of the system maybe can change over time. And so far we've talked about the secret and the specification being defined at the start. And then we somehow reveal the secrets, or we check the specification, we do all these things, and then we sort of continue. But is it really the case that nothing changes over time in terms of whether we want to redefine our specifications or we want to redefine our secrets after they are revealed? Is it something that is studied, or is it something that has some practical applications in security or in other domains?
So in robotics, people talk about iterative planning, which is that this view is that you have all the information, you come up with the strategy, and then you leave till kingdom come with the strategy, and nothing changes, doesn't quite match reality. For example, a robot, let's suppose, has to clean all the rooms in the building after 5 o'clock. After all left, the robot will come and clean all the room. And the robot comes, and one of the rooms is locked. So it can sit there and just wait forever, or to say, you know what, I'm not going to clean that room today. So there is this concept of iterative planning, where something happened and you have to kind of revise your specification. And even the question is, okay, what is a reasonable notion of approximately? I know now that I cannot, that more information has been revealed to me. I know that the earlier specification is not realizable. What is a good approximation for me to realize now? So we come under iterative synthesis or iterative planning. But it more happens, I've seen in the robotics community, not so much in the formal methods community, where we like cleaner models and beautiful mathematics. And when something is true, it will be true forever.
So there is live synthesis that Niklas worked on a few years ago, right? Where the idea is that you have a running system and then you have a new specification, and you need to transition your running system into the new specification, so that at some point the new specification needs to become valid. And there's the interesting issue that there may be obligations that still come from the old specification that need to be satisfied because you can truly satisfy the new specification. So I think that's very interesting, especially if you have, continuing controllers that don't really terminate, and where you want to change some aspects of the behavior as you go along.
But is it, so can we say something formally about this?
Mike, I can't hear these guys.
So what can we do in terms of modeling and like formal guarantees in this case? Or is it, do we always have to resort to something approximate?
Live synthesis has the same guarantees as standard synthesis. I mean, it may become, I mean, your new specification may be unrealizable in the current state of your system, but you will know for sure. If it's realizable, then there's a strategy that takes you over.
I will just add that for me, the question is similar to the question of who synthesizes the specification, which is a criticism we often hear about synthesis. Yes, so we know how to transfer specs to implementations. Coming up with the right spec is also important, but it's different. But of course, there are good reasons to combine it. But the question of coming up with good specifications is a real challenge. And so there is work about coverage and vacuity. So the effort is really to reason about specifications.
Okay, now we turn this side.
Hi, Moshe. I wanted to get a perspective on the complexity of LTL synthesis. The double exponential size of the implementation doesn't seem so bad if you look at existing systems, perhaps manually written ones, right? If you take the size of the specification, you create exponentially many computer words. Each of the words can have exponential states. So that gives you a system with doubly exponential states. Am I right, or am I missing something?
So there is some work on what people call synthesis for kind of succinct systems, which is okay, the strategy is of double exponential size. But maybe there is a circuit of exponential size that will have exponentially many, double exponentially many states. So maybe I have a succinct strategy. And there's a complex argument why this is not likely. Because if there is a succinct circuit, then here is how I will do synthesis. I will guess such a circuit, and then I'll just model check it. But then I'll get an algorithm which is in exponential space. And if we believe that x space is different than 2x time, I mean, there are systems that not only double exponentially many states, but even if you have a succinct representation like a circuit, a sequential circuit, it will still have to be of a large size. So this is just, so in terms of worst case complexity, there's no salvation by saying, okay, we'll have a succinct representation. So there are specifications that, I mean, it's kind of the same thing we discover with the halting problem. It's undecidable. But most, I mean, we have very good success with termination detection, because most programs that diverge don't diverge for deep mathematical reasons. They diverge for stupid reasons, okay? Because the program made a stupid mistake, not because of the status of the Poincaré conjecture, okay? And so we are very good actually in checking termination of real programs. So the hope is that for real specifications, whatever that vague term means, we will not get this worst case complexity. The same thing we know that going from LTL to automata will be in the worst case exponential, and that could kill us. But in just practice, unless you write very convoluted properties, it just doesn't happen. So it's a fuzzy answer, because that's really, to me, one of the great challenges that we have. To me, one of the most beautiful theory in computer science, complexity theory. And we're more and more discovering that it's actually a fairly poor guide to how algorithms behave in the real world.
I would just also add that unlike verification, where we can decompose the specification, a related challenge in synthesis is that you want a system that would satisfy a conjunction of many, many specifications. So this bound is even more painful.
But there are work on incremental synthesis. There are work that try to address this.
But
The
it's
fact
still,
that yes, in the worst case, we are all dead. Okay, and now the question is what happened in real life.
Before I would like to ask a question, a general one.
Closer.
Even closer. Okay. What should we synthesize? So you can say finite automata, C programs, timed automata, Markov decision processes, Petri nets. Well, easy answer is anything you like, but I would like to know what models that you find most promising.
Depends on the application. I don't know that there is a universal answer. Even
No, just in a year or two from now, if you stay with finite automata, it's fine for me also. It's just a question.
You have a better insight than mine, other than it depends?
I think it depends very much on the purpose. Why do you do synthesis, right? And the motivation for doing that varies wildly. I mean, some people do it to actually generate programs, and that then you have a particular domain in mind. So for example, if you're synthesizing a smart contract, that's going to be very different from when you synthesize a controller, right? You need to be in the right expressiveness class. In other circumstances, you do synthesis in order to prove that something can't be done, right? So you're saying that, like in the CAP theorem, that you can't be consistent, available, and partition tolerant at the same time. Then it's not so relevant that you express that hypothetical program in a particular programming language, but you want to say that there's a fundamental reason why these requirements can't be satisfied at the same time. So I think, as Moshe said, it depends on what you're trying to do, but in the end, you probably want to have a target language that meets your application domain. Personal. Okay.
We want to synthesize monitors.
Okay, I can live with that answer. Monitor components are one really interesting application domain. Yes.
So what are the models that are most useful?
I'm sorry, for
the
monitor?
Models that are most useful in that setting.
In the setting of monitoring.
Yes.
So I think there I need to go back one step. So I think Moshe said earlier that we have to scale down a little bit in order to have more impact. And I think monitoring is one of those step downs where we first of all don't even try to come up with a strategy, but just to determine if there is a need to execute a particular strategy. And then you go into an application domain, let's say aerospace, when you look at aircraft, and you need to determine if the aircraft is in a safe state. So that means you need a very expressive language in order to do the calculations necessary to do that. So our answer here is RT-Lola, which is a really expressive real-time language, way more expressive than LTL and company, but apparently sufficiently expressive that the engineers can express what it means for an aircraft to be safe. And the great benefit of a language like this is that you can still translate it automatically into a monitoring application. You can run it on an FPGA, for example, and run it very effectively on an aircraft. And you have the formal connection to the specification. You're guaranteed that it will monitor the specification under all circumstances. So I think this is the exact right type of match between the formal specification language and the application domain, because if you're observing aircraft, then you need to have this radical notion of expressiveness. Now, once the monitor determines that there's an emergency situation and you need to find an contingency strategy, you might very well go back to finite automata in order to describe that strategy. But these are like completely separate issues.
Okay.
I have a memory of Amir Pnoeli having a pendant with a chip on it. That was, no?
Roderick prepared this. Roderick Bloom prepared the
Roderick
chip.
Bloom had all the way, took it all the way down to an actual, even produced, went to and produced the chip. So that's one goal. If you want to have a nice pendant, and you can say, I synthesize by pendant, there is a way to do it.
Okay, last question, because we are already into our break. So who? He's closer.
Okay, so I mean, here we are talking about synthesis where there is a specification, and we say that every run must satisfy. I mean, it's in some sense an absolute satisfaction of the property. So, is there a notion of approximate synthesis where we talk about, I mean, is there any work? Does it even make sense? Because I guess in a lot of real life situations,
but you have, for this you have to go to probabilistic model, and you go to the word, let's say, of MDPs, Markov decision processes, and then you can say, I want the probability, I want the strategies for the probability that this property will hold with a certain probability. Okay, so you can decide what is the probability, and that we have technology how to do that.
So even in the qualitative setting, there are notions of approximative synthesis, where, so for example, best effort synthesis, where you satisfy the goal whenever possible, but sometimes you don't. And then also these approximative notions where you prefer to cover a larger space of inputs over a smaller space of inputs, and you try to cover, essentially optimize the density of the space where your specification is being covered. So, for example, there's work by Finkbeiner on this.
And even iterative planning I mentioned before, you realize the specification was not realizable. And then you say, okay, it's kind of a bit of a best effort, but a different notion of best effort. Okay, what would be my new property that will be as close as possible to the previous property? And I'll try now to synthesize for that.
And with that, let's give a round of applause to our panelists. And please continue discussion at the coffee break.